All right, so the Bayesians. So here are some famous Bayesians. Hugo Pearl, within computer science is probably the most famous one. He actually won the Turing Award, the Nobel Prize of Computer Science a few years ago for inventing something called Bayesian networks, which is one very powerful type of Bayesian model where, it's a big graph where each node is a variable and then the edges between the nodes represent dependencies between the variables. Two other famous Bayesians are David Heckerman and Mike Jordan. Bayesians are known in machine learning as the most fanatical of all of the five tribes, right? They really have a near religious devotion to their paradigm. And, they're the first ones to say so. And I think the reason for this is that, Bayesians have their origins in statistics, and for 200 years, Bayesians were a persecuted minority in statistics, right? So they had to become very hardcore in order to survive. And it's a good thing that they did survive because they have a lot to contribute. And these days, with computers and, algorithms like Markov chain Monte Carlo and large data and whatnot, they're actually on the ascendant in statistics. So what is the basic idea behind Bayesian learning? Well, the basic idea is that, as I said, everything that you learn is uncertain. So what you have to do is compute the probability of each one of your hypotheses and then update it as new evidence comes in. And the way you do that is with Bayes' theorem, okay? And Bayesians love Bayes' theorem so much that there was this Bayesian machine learning startup that actually had a neon sign of Bayes' theorem made, and then they stuck it, outside their office. Okay, so this is like, Bayes' theorem in big neon letters. Okay, so how does Bayes' theorem work? Bayes' theorem is actually, incredibly simple. It's so simple, it's barely worth being. It would be barely worth calling a theorem if it wasn't so important. So the idea is this. So, let's suppose that you have all your hypotheses, right? You define your space of hypotheses in some way. It could be, for example, the set of all Bayesian networks, or the set of all, neural networks, or all decision trees, or whatever. And now the first thing that you're going to have is a prior probability for each hypothesis. This is how much you believe in that hypothesis before you've even seen any data. Okay? And this is actually what makes Bayesian learning very controversial, is that many statisticians say, well, you have no grounds on which to just make up a prior. And the Bayesian's answer to that is like, you have to make that up, whether explicitly or implicitly, so let's just be explicit about it. Okay? So the prior is how much you believe in each hypothesis before you see the evidence. But then what happens is that as the evidence comes in, you update the probability of each hypothesis. A hypothesis that is consistent with the data will see its probability go up. A hypothesis that is inconsistent with the data will see its probability go down. Okay? And the consistency of the hypothesis of the data is measured by what's called the likelihood function, which is the probability of seeing the data if the hypothesis is true. Okay? And this here is actually no different from frequentist statistics and the maximum likelihood principle, which is basically saying that if your hypothesis makes what you're seeing likely, then conversely, what you're seeing makes your hypothesis likely, okay? And the Bayesians incorporate that in the likelihood. And the product of the likelihood and the prior is just the posterior, which is how much you believe the hypothesis after you've seen the evidence. So as you see more evidence, the probabilities evolve, and hopefully at the end of the day, one hypothesis will come out as clearly better than the others, but that won't necessarily be the case. You might still be entertaining a lot of hypotheses even after you've seen a lot of data, okay? There's also the marginal, which is just something that you have to divide by to make sure that the probabilities add up to 1. So, let's not worry about it for now.